So here, whenever you're opening your visual CEM, and then here you have to click on applications, you have to select mesh. So once you select mesh, then you can just click on new file so that it will be opening your new file. So opening your visual CEM software application, selecting your mesh window in order to get started with the mesh part, and then select new file in order to open this particular user interface. So we have got this. Now let us just go ahead with this particular design file. So here the example, whatever I would like to show it, it's a half wavelength dipole. Half wavelength dipole in the sense it's also called as lambda by 2. Why it is called as half wavelength dipole also I'll tell you. I'll show you some resources on that. So the complete length you can note down. You can get started with noting down. So you can see if the complete length of the antenna is mentioned as 337.8 mm. So this is after calculation. Okay, 337.8 mm, and it's half, and it is a half wavelength long at 443.7 megahertz. So the frequency of operation. So you have to note down the frequency of operation also. That is 443.7 megahertz. And the dipole is located along the z-axis with the radius of 1 mm. And the excitation used in the analysis is delta gap. So basically, whenever you're going for dipole or monopole, or else if you have a node-based implementation, we'll be always going with the delta gap voltage source with a voltage of 1 plus J0. And at the midpoint of the dipole, done. So the analysis is done with the linear frequency intervals of 21 frequencies from 433.7 megahertz to 453.7 megahertz. So this is a detailed description of the problem. So if you see, we have got 337.8 mm and then F0 is 443.7 megahertz. So we have noted down the required parameters. But how exactly we came across the length, and how exactly when you have selected your frequency, how exactly you have came across the length? That is what is a major thing what we have to check it out. So let us just check it out how exactly we have to go about. So before that, I'll just open a Wikipedia page on a dipole. So in order to give you some description on dipole. Yeah, so dipole antenna, in the sense, it's nothing but you will be, as a name itself suggests, it has two poles, two polarities, two poles with which your electromagnetic radiation comes across. So simply, if you are taking a transmission line, if you are truncating a transmission line, basically your transmission line starts exciting. So how exactly this electromagnetic radiation will excite is, so when you put some truncations, when you put some tapering on your particular electromagnetic wire or else transmission line wire, then it actually changes some parameters of your particular transmission line and it leaks the electromagnetic radiation around the part. So antenna is a transducer which actually takes the voltage as a signal, voltage or power signal, and converts that into electromagnetic radiation, emits that into an air, and through air it receives to another end wherever the impedance matching is properly done. Then the reception is done. The signal reception is done in terms of electromagnetic radiation. After that, it will be you will be able to receive the inputs. So that is how your antenna will get some linkage. What exactly is dipole all about? So dipole antenna, as the name itself says, it has two polarities. So we will be actually exciting. If you see, we have different type of dipole antennas. So we will be actually exciting exactly at the center of the dipole antenna. So when we excite at the center of the dipole antenna, and when we are trying to give some feed for the dipole antenna, it actually takes the sinusoidal signal as an input, and then it generates a pattern around your left pole and right pole in the sinusoidal format. I mean, you'll be getting a 8 pattern around your particular dipole antenna. Why 8 pattern also I'll tell you. this dipole antenna is nothing but it's an omnidirectional antenna. So the coverage of this particular antenna is in all directions. So Yagi-Uda antenna is a olden day antenna, which actually uses the concept of dipole only. So we have different type of dipoles, short dipole, dipole antennas of different lengths. You can see we have based on the dipole lengths, you'll be actually getting the different type of results. If you see, if you're going for less than lambda by 2, then your gain will be very less and efficiency is too low. 0.5 lambda, most commonly you'll be getting somewhere like 2.2, 2.15 dB of gain. Similarly, 1 lambda size, if you're trying to generate, you will be getting a fat dipoles. The gain will be also high. Similarly, if you're going for 1.25, you'll be getting furthermore high. If you're going for 1.5, again, the gain will be reduced. If you're going for two times of wavelength, if you're trying to design, it doesn't work as lambda, it doesn't work as dipole. The basic drawback what dipole has is the length of dipole will vary with respect to the wavelength. So if you're going for higher frequencies, if you're going for a lower frequencies, the complete length of the dipole will vary. If I'm going for a lower frequencies, what happens is I'll be getting a higher wavelength, then I have to prepare an antenna which is of very long length. Similarly, if I'm going for higher frequencies, I'll get in a vice versa manner, I'll be getting it. So the simple calculation what we'll be doing here is F is equal to C by lambda. That is what is the calculation we'll be doing it, wherein with we'll be actually getting the lambda value. So this is how your dipole will actually work. Okay, so you'll be exciting with a source. Either it could be delta gap source or any other source. So we'll be actually getting a 8-shaped pattern around your particular dipole antenna. So this is half-wave dipole antenna. Similarly, we have folded dipole and the other variants as well. And this is the pattern. It's a 3D dimensional pattern, whatever we'll be actually getting it for your dipole antenna. And this is your 2D patterns, what we'll be getting it. Like 8-shaped pattern, you'll be getting it in a non-linear scale, where it shows the isotropic behavior of the antenna. So it shows your antenna covers up throughout the regions. So that is how actually you have to analyze the antenna. So this is how you have to get started with. And then similarly, in order to give the excitation also, there should be a line, transmission line with some bend. It has to accept the characteristic impedance of 50 ohms. So whenever one of the important concept in antenna theory is, if there is a proper antenna matching, then only the proper signal could be sent out. If there is no proper matching, what happens is the complete signal will get reflected back. You will be getting a return loss. So these all are the things what we have to analyze. We have to put all those things into consideration. So this is how your dipole will start rotating. So pole 1, pole 2. So electromagnetic radiations will expand in this particular direction. So these are the electrical field lines and these are the magnetic field lines. So electromagnetic field lines are spreading in the omnidirectional fashion. So these glyphs actually helps us out in understanding how exactly we are getting started with different sort of design. Now let us just go ahead with the same design whatever we have gone with. So let us just calculate the wavelength for 443.7 megahertz.
Rohit sir.
Yes sir.
Is it?
Yes sir. Yes sir. I'll do that. Now are you able to see the screen, sir?
Yeah. Now, sir. Okay.
Yeah. Thank you, sir. Now let us just go for calculator. Let us just have a reading how exactly we are actually getting it for. Getting the wavelength for this particular design, whatever we are going with. Okay. and later in which you can also do this kind of design with your own measurements. Yeah, now I want to calculate for 443.7 megahertz, right? So it's 3 into 10 to the power of 8. So what I'll directly do is, so 3 into 10 to the power of 8, already I've done it. So divided by yeah, so 3 into 10 to the power of 8 divided by 443.7 megahertz, right? So 443.7 443.7 into So the desired frequency is 443.7 megahertz. So you have to divide your C value. C value in the sense it's nothing but 3 into 10 to the power of 8. So that's the reason I've took this. Then divide by 443.7 into 6 10 power. So here I'm getting 0.6761325 meters. So if I convert this into in terms of millimeters, so I'm getting lambda value, I'm getting somewhere like 676.1325. So if I divide this by 2, approximately it would be 338.06625 or 337.8. Approximately the same length has been taken. So in this way, we have to actually consider this particular length of the half wavelength dipole. So this is how we'll be actually calculating. So for whatever antennas you are going with, wherever there is a dependency on lambda, you have to go ahead with this kind of procedure. So the accuracy, why exactly we have to 337.8 is basically when you're going for this kind of designs, if you're going for a theoretical formula, there would be a small deviation in the performance. So if you are taking a slight less when compared to the actual calculated formula, you will be getting a perfect performance at that particular frequency. Okay, so here if you see, we have set it up to 337.8 mm. So this is my length. So I can completely operate this particular antenna now. And the complete radius, what you can see, it is for 1 mm. So note down these kind of parameters, whatever we have, and then get started with the things. So as of now, I'm opening the software. So in order to get started with the dipole antenna, so we can directly get started with this particular node option. You can go to